All right, so we're going to start this out with like not exactly a meme, but something I thought was kind of funny, right? It looks like text messages where one person says, "Are you awake?" The other person says, "Yeah, LOL." And the first person says, "Good. I need to talk about why d dx of e to the x is e to the x," right? And I think this is funny because it does kind of remind us that the big deal about e to the x, right, is that it's the only function that it's its own derivative, right? And so by definition, its own antiderivative. And that's a pretty big deal. And I could see how the nerdy part of you might have to stay up nights to think about that. All right, so we're going to use that fact in doing a little development here. Number 1 says, write the equation of the tangent line to the function y equals e to the x at x equals 0. Check out the graph. All right, so let's see if I can be cool and do a little reveal here. Ha. All right, so equation of the tangent line, right? We've talked about this a lot of times in class. You need two things. You need a point and you need a slope, okay? AKA the derivative at that point. And so what's the point we need? Well, we know any single point is x comma y, and here we know that x is 0 because I told you that right here. Okay, and then it would be y of 0, which in this case would be e to the 0 power. Well, e to the 0 power is just 1. So I have the ordered pair 0, 1, and then the slope would be y prime at the x value of 0. And so we can use what we just talked about, the fact that y prime in general of e to the x would just be e to the x, and so y prime of 0 would just be e to the 0 or 1. Okay, so we have enough to go ahead and write the equation of the tangent line, right? Y equals the slope times x minus the x value plus the y value. And it probably makes more sense to simplify this to y equals x plus 1. And so this would be the equation of the tangent line. So we know, right, that if we graphed it, what would we see? We would see this line, right, touching the curve e to the x at 0 as a tangent line. Okay, all right, oops. And so the whole idea of the tangent line is the original function acts like that line, but only for points really, really close to the point of tangency. Okay, aka in this case, the point of tangency is for x values near 0. Okay. So what we're saying is really, really close to 0, e to the x is approximately the same as the line x equals 1. Okay, but we'd like to have a better approximation of e to the x, and so one way we can do that, right, is to take what I have, and I am going to take the integral of both sides. All right, so on this side, I'm still going to have e to the x, and then over here, I'm going to have 1/2 x squared plus x plus c. Okay, I do know one ordered pair, right, that we know for sure is on this graph, and that is when x equals 0, y equals 1, and that we know that from the ordered pair that we used to make the equation of the tangent line. And so if I make that substitution when x is 0, right, this would be 1, and this would be 0 plus 0 plus c, and so therefore c equals 1, and so my new approximation of e to the x is 1/2 x squared plus x plus 1. Okay, and so I'm going to get tricky here since I never can do this in class, right? I'm going to do the exact same thing again. Okay, so what happens if I now switch colors and I take the integral of this? Okay, well, I'm still going to have e to the x on this side. I'm going to have, what will I have here? Let's see, 1 over 2 times 3x cubed plus 1/2 x squared plus x plus c. I can still use that same ordered pair because I know for sure it's on the graph. What's going to happen is I'm going to get e to the 0, 1, all of these things will be 0 because they all have x's in them. And then I'm going to have c. And so c is going to be 1. In fact, every single time this happens, I'm going to have all x's, right, on this side of the equation with the c, and this is always going to be 1. And so it turns out that c always equals 1 in this situation, so I'm not going to probably write it again. I will just say from this point on, we're going to continue to say that it's 1. So right now I'm at e to the x is approximately 1 over 2 times 3x cubed. I know you might want to be simplifying that. I'm going to encourage you not to, again, for pattern finding reasons. And so what happens if we do it again? So I'm going to take the antiderivative of this. If I do it again, then I'm going to get e to the x on this side. This time I'm going to have 1 over the 2 times 3 that was already there times the new power for x to the 4th plus 1 over 2 times 3 x cubed plus 1/2 x squared plus x, and then plus the c value, which we know would turn out to be 1. Okay. Could I do it again? Of course I could. Right? Who wouldn't like to do this again? So let's see. I have e to the x is approximately, this would be the 2, the 3, the 4 that was already there, and then divided by the new power, so then times 5, x to the 5th, plus 1 over 2 times 3 times the new power 4, x to the 4th, plus 1 over 2 times 3 x cubed, plus 1 over 2 x squared, plus x, plus the c value that we know would be 1. Okay. And so I can continue on, right? I probably don't even need to do another integral. Maybe we could just write down what we would see if we did another integral. Okay, be 1 over 2 times 3 times 4 times 5 times 6 x to the 6th plus 1 over 2 times 3 times 4 times 5 x to the 5th plus 1 over 2 times 3 times 4 x to the 4th plus 1 over 2 times 3 x cubed plus 1 over 2 x squared plus x plus the c value, which would be 1. And so my question is, what pattern are we seeing? Okay, well, let's take a look at this. What is 2 times 3 times 4 times 5 times 6? I could multiply it out, or instead, I can represent it as 6 factorial, right? What is 2 times 3 times 4 times 5? Well, that is 5 factorial. 2 times 3 times 4, 4 factorial. This one's 3 factorial. This is 2 factorial. And technically, this is being divided by 1 factorial, right? Because 1 factorial is just 1. And even this one, 0 factorial, because 0 factorial is still 1. So can I generalize? Well, it seems like I should be able to, right? My generalization would be e to the x. And I'm going to start flipping it around because we know 1 is always a part of this. 1 plus x plus x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial. And how many times do you think we could integrate it? It feels like we could integrate it forever. Okay, and so what is the general pattern that we're finding? Well, it seems like on the top I have an x to the n, and on the bottom I have n factorial, right? If I want to write it with series notation, it's basically that general rule we just found, and if I start it at n equals 0, I get that. And so, pretty cool, right? What we just found out is you literally can represent the function e to the x with an infinite series. And then we're going to talk about what does that look like in the new context of 9.7.